Hello everyone and welcome back to the Calculus 1 video lecture series. Today we are going to be covering one of the most important of derivative rules called the chain rule. So for the chain rule, you have learned how to take the derivatives of products and quotients so far. You use the product rule to take the derivative of a product. You use the quotient rule to take the derivative of a quotient. The chain rule is used to take the derivative of a composition of functions. So the chain rule can be used on any function composition, and remember you can compose more than two functions, so the chain rule can be used on as many function compositions as you want. Now just to recap function composition, let's say that you have two functions, f of x, which is 2x minus 5, and g of x, which is the square root of x. A function composition looks something like this. So g composed with f of x means that you are taking the entire function f of x and you are plugging it into the variable in the function called g. So g composed with f is also known as g of f of x, which means that you take the entire function f and you plug it into the variable in g. So in this case, g composed with f would be the square root of 2x minus 5. Now, order matters with function composition. So if you do f composed with g of x, what you're actually finding is f of g of x, which means that g is the inside function this time and f is the outside function. So f composed with g, you're going to take the entire g function and plug it into the variable in the f function, which is 2 square root of x minus 5. So the key with chain rule is you're going to be using chain rule to take the derivatives of functions like this especially. And the key with chain rule is being able to identify the inside function and the outside function, and being able to identify what function was plugged into what. So in this case, the 2x minus 5 is the inside function because it was plugged into the square root function. So 2x minus 5 would be the inside function, and the square root would be the outside function. So as long as you can identify the inside function and the outside function, chain rule is easy because you have to remember that function compositions are like onions in the fact that they are layers. So composed functions are multiple functions that are all stacked inside of each other. And chain rule is really easy to do as long as you can identify each individual layer and each individual function and identify what function is on the outside, what function is on the inside. So, taking derivatives of compositions using chain rule is like an onion. Like an onion, you will peel away at the function by deriving one layer at a time. Just like you peel an onion by peeling away the outside layer, then the next layer, then you work your way in. Chain rule is going to be the same way. You're going to start with the outermost function and you're going to peel it away by taking its derivative and work your way in one function at a time. So this is the actual definition of the chain rule. I'm going to show you a more intuitive version of this. So if you have two differentiable functions and a composition has happened, f composed with g of x. F composed with g is also known as f of g of x, which means that g of x was the inside function and f was the outside function. So if this composition is differentiable, then its derivative is going to be f prime composed with g of x times g prime of x. So we're going to break this down one piece at a time. So f prime, you start with the derivative of the outside. And notice you are composing it with the inside left completely alone. Remember, like peeling an onion, you peel away one layer at a time, you derive one layer at a time. So you start with the derivative of the outside composed with the inside left alone. Then you multiply it by g prime, which is the derivative of the inside function. So the chain rule is going to be the derivative of the outside composed with the inside left alone times the derivative of the inside function. So let's find the derivative of this function composition here. Now, the only way to avoid chain rule would be to expand this out 10 times, which I'm sure nobody wants to do. So we're going to take this derivative using the chain rule. So you have to identify what is the outside function and what is the inside function. The outside function appears to be this exponent of 10. So the outside function is some polynomial of degree 10. That means the inside function is the 6x cubed plus 3x plus 1. So with chain rule, you're going to start off with the derivative of the inside. So you're going to pretend that the inside function is just a variable. How do you take the derivative of a variable raised to the 10th power? Well, since this outside function is a numeric power of 10, its derivative is going to use the power rule. So we're going to use power rule to take the derivative of the outside, which means we would move down the power, and then we would decrease the power by 1. Now remember, we're only deriving one function at a time. So that was the derivative of the outside composed with the inside function left completely alone. Then we're going to multiply it by the derivative of the inside function. So now we're going to multiply it by the derivative of 6x cubed plus 3x plus 1, which is 18x squared plus 3. And please use parentheses if the derivative of the inside involves more than one term. And I am not going to ask you to expand anything out 9 times, so this is fully as simplified as it needs to be. So what we're going to do is we are going to find the derivatives of each of these using the chain rule. So starting with this first one, I am going to do a little bit of rewriting first. I'm going to rewrite that square root as an exponent of 1/2. So I'm going to rewrite this as 5x squared plus 1, all to the power of 1/2, and we're going to take its derivative. So we're going to need to identify the outside function and the inside function. So the outside function, overall, this is a square root. So the outside function is this exponent of 1/2. That means the inside function was everything that was inside the square root, which is this 5x squared plus 1. So with chain rule, you always start with the derivative of the outside. So you pretend like the inside function isn't there. And you're going to take the derivative of the outside using power rule like you normally would. So derivative of the outside, we're going to move down the power and decrease the power by 1. Then we're going to compose it with the inside function left completely alone. Then we're going to multiply this by the derivative of the inside function, which is 10x. And then if you want to, half of 10 is 5, so you can write this as 5x over the square root of 5x squared plus 1 if you want to. You don't need to simplify any more than that. So then for the next one, we're going to be taking the derivative of this quotient all raised to the 3rd power. Now, the parentheses around the outside means that the entire quotient is being raised to the 3rd power. So what we're going to do is we are going to use chain rule to take this derivative. So the outside function is this exponent of 3. The inside function is everything here that was being raised to the 3rd power, so the inside function is that quotient. So overall, since this is overall a function composition, overall you will need chain rule. Now within chain rule, when you get to the derivative of the inside, you are going to need quotient rule to take the derivative of the inside. But chain rule requires that you do one thing at a time, so we're going to start with the derivative of the outside. So we're going to pretend like the inside function isn't there, And we're going to take the derivative as if this was just a single variable raised to the third power. So since this 3 is a numeric exponent, we're going to use power rule to take its derivative. So we're going to move down the power and decrease the power by 1. And we're going to leave the inside completely alone. That's a 3t, oh boy, squared plus 2. We're being very glitchy today, apparently. Sorry about that. Then that was the derivative of the outside with the inside left alone. Then we're going to multiply it by the derivative of the inside. So the derivative of the inside is going to require quotient rule. So 5t squared is the top function and 3t squared plus 2 is the bottom function. So for quotient rule, we're going to start with the bottom function left alone, 3t squared plus 2. Then we're going to multiply it by the derivative of the top, which is 10t. Then minus the top function, 5t squared, times the derivative of the bottom, which is going to be 6t. Then we're going to divide all of that by 3t squared plus 2, the entire bottom function squared. Then if you were to simplify this, first you would get this 3 times, if you are going to multiply something by itself, remember, if you are squaring a fraction, you can simply square the numerator and square the denominator. So if you square the numerator, you get 25t to the fourth, all over parentheses 3t squared plus 2 squared. And then if you multiply it by, let's simplify this a little bit. 10t times 3t squared is going to be 30t cubed. And then this is going to be plus 20t. And then minus 5t squared times 6t is 30t cubed, all over 3t squared plus 2 squared. So when those cancel out, and you can just simply multiply across, so 3 times 25t to the fourth times 20t is going to be 1500t to the fifth, all over 3t squared plus 2 squared times another 3t squared plus 2 squared is 3t squared plus 2 all to the fourth power. So that is actually how it would fully simplify. So then for this last one is actually a function composition. Because any time that you have an exponential function and there is anything other than just x in your exponent, it's technically a composition. So this e to the negative 3x, because the exponent is something other than just x, this is a composition and therefore requires the chain rule. So overall, this is an exponential function of base e. And within that exponential function, you have this negative 3x. So this negative 3x, which is in place of the regular variable exponent, this is actually the inside function. The outside function is the overall structure, which is the exponential of base e. So the outside function is that exponential of base e. So when you take the derivative of the outside function is an exponential of base e. So you're going to pretend like the inside function isn't there. You're going to pretend that this is e to some variable power. The derivative of e to the x is itself. So the derivative of the outside is itself with the inside left alone. Then you're going to multiply it by the derivative of the inside, which is negative 3, which gives you a derivative of negative 3 e to the negative 3x. So it was a small function composition, but anytime you have e to any power other than just x, it does require the chain rule, where the outside function is the exponential of base e, and the inside function is that exponent. So then we're going to calculate this next derivative. So we're going to calculate the derivative of x squared plus 7x plus 2, all raised to the power of negative 1/3. Remember, if at any point in this video you want to attempt a problem before I do it, just feel free to pause the video and resume it when you are done working. So then we're going to identify the inside function and the outside function. So the outside function is going to be this exponent of negative 1/3. The inside function is everything that was being raised to the power of negative 1/3, so this is the inside function. So when we're going to use chain rule, we're always going to start with the derivative of the outside function. So we're going to pretend that the inside function isn't there. We're going to pretend that this is some variable raised to the power of negative 1/3. So how do we take the derivative of x to a numeric power? We use the power rule. So the derivative of the outside, we're going to move down the power, leave the inside alone, and decrease the power by 1 gives us negative 4/3. And remember, when you're taking the derivative of the outside, you're going to leave the inside alone. Then we're going to multiply that by the derivative of the inside, which is 2x plus 7. And no, you don't need to simplify that any further. That is good enough. So then for this next one, we're going to be calculating the derivative of the tangent of x over x plus 1. Now, anytime that you have a trig function and inside of that trig function you have anything other than just x, it does require chain rule. So the outside function is this tangent, and the inside function is everything that is inside the tangent, which is x over x plus 1. So we're going to start with the derivative of the outside function. The derivative of tangent is secant squared. And then remember, leave the inside alone for right now. Then you're going to multiply it by the derivative of the inside. Now, the derivative of the inside is a quotient and it requires quotient rule. So you're going to use quotient rule just for the derivative of the inside. So we're going to start off with the bottom function left alone times the derivative of the top. Derivative of x is 1. Minus the top function x times derivative of the bottom. Derivative of x plus 1 is 1. All over the bottom function, x plus 1 squared. And then yes, this simplifies down quite a bit. This can simplify down as secant squared of x over x plus 1 all over, so times 1 over x plus 1 squared. And because this x plus 1 is inside of a secant and this x plus 1 squared is not inside of a secant, you can't actually combine these and you can't simplify that to x plus 1 cubed. So this is as good as it's going to get. You can't combine something that's inside of a secant with something that is not inside of a secant. Now remember, chain rule can be used on any number of function compositions, and it is possible to have 3 composed functions. This just means that you have 3 layers of functions. And chain rule still works as long as you start with the outermost layer and you take the derivative one function at a time, working your way in. And remember, when you're taking the derivative of a particular layer, you leave all of the inside functions completely alone. So there are actually 3 functions here that have been composed. We have a sine, we have an exponential of base e, and we have this x squared. Remember, anytime that you have e to the anything other than just x, it is a composition. So we're going to start with the outermost function, which I think is obvious. Sine is the outermost function. Now inside the sine, we have this e to the x squared. Remember, when you have an e to any power other than just x, the outside function would be the exponential base e, and the inside function would be the exponent. So this exponential of base e is the middle function, which means this x squared that's inside that exponent of e, that is the inner function, or the innermost function. So we have 3 layers here. We have the outer layer, which is the sine. We have the middle layer, which is the exponential of base e. And we have the inner layer, which is the x squared. And we're going to use chain rule to take the derivative one function at a time. And you start with the outermost function, so we're going to start with sine. So the derivative of sine is cosine. Now, the only one I'm taking the derivative of right now is the outer function, which means I need to leave all of the other functions completely alone. So I'm going to leave the e to the x squared completely alone. So now that we've taken the derivative of sine, we can peel that away, and now we're going to focus on e to the x squared. So next, we're going to take the derivative of just the middle function. So the derivative of e to a power is e to that power, so e to the power of x squared is the derivative of the middle function with the inner function left alone. Now that we've taken the derivative of the middle function, we can peel that away, and now we're going to take the derivative of the inner function, so the derivative of x squared is 2x. No, this does not simplify any more than that. That is your final answer. So just remember that when you're using chain rule, you are going to only take the derivative one layer at a time and leave all inside layers completely alone until you're ready to take their derivatives. Now, for those last several examples, overall, they were all function compositions. That is not always going to happen. There's not always going to be a case where chain rule is basically the only rule you use. You can have other rules in conjunction with chain rule. So we're going to calculate the derivative of this function, x squared times the square root of x squared plus 1. Overall, this is a product. So overall, this is going to require the product rule, where x squared is the first part of the product and square root of x squared plus 1 is the second part of the product. So derivative of the first part of the product is going to be pretty straightforward. The second part of the product is going to require the chain rule. So the chain rule is not needed for the entire thing here. The chain rule is only needed for the derivative of the second part of the product. So chain rule is only needed for a second part of the product. So let's start by using power rule. So we're going to start off with the derivative of the first part of the product, which is 2x, times the second part of the product left alone. Then we're going to add to it the first part of the product left alone, times the derivative of the second part of the product, which, if it helps, you can always rewrite that square root as an exponent of 1/2. So for the derivative of the second part of the product, this power of 1/2 is the outside function, and x squared plus 1, everything underneath the square root, was the inside function. So for the derivative of the second part of the product, we're going to start with the derivative of the outside function, which is move down the power, leave the inside alone, and decrease the power by 1. Then you multiply it by the derivative of the inside, which is 2x. And then, half of 2 can cancel out, leaving you with 2x times the square root of x squared plus 1. Plus x squared times x is x cubed, and you can write that all over the square root of x squared plus 1. And then, in order to simplify this further, you would need to find common denominators and add the two fractions together and actually simplify the numerators. Fully simplified, since we're running out of room, fully simplified, this would be 3x cubed plus 2x all over the square root of x squared plus 1. So just find common denominators and simplify the numerators. This is, well, what it looks like fully simplified. Sorry about that. All right, so that is going to be it for chain rule. Chain rule is used anytime you take the derivative of a composition. No matter where that composition appears, you need to use chain rule to take its derivative. So thank you all very much for watching. In the next video, we are going to be covering a major application of the chain rule, which is a process called implicit differentiation. So I look forward to seeing you in the next video, and thank you all very much for watching. Bye-bye.